Hello everyone. We'll be starting with flow through pipes, which is module number 5 of fluid mechanics subject. We'll straight away go. There are many things to be learned which are interesting really, and then which will be of great help and use in studying many further subjects. And even on the field application of this is very much is there. So we'll go ahead. This is in module number 5, flow through pipes, and then surge analysis in pipes. There are two parts. First one is flow through pipes. There is an introduction, major and minor losses in pipes, Darcy-Weisbach equation for head loss, very important equation, right, which is a head loss, energy loss in pipe due to friction in pipes in series and pipes in parallel, equivalent pipe problems. Then you have minor losses in pipe flow, equation for head loss due to sudden expansion, numerical problems on all these concepts, hydraulic gradient line, energy gradient line, numerical problems on that. Then you have pipe networks, Hardy-Cross method, but no numerical problems are involved as far as pipe networks is concerned. Anyway, it is not too complicated, but anyway, it is not included. Surge analysis in pipes, water hammer, what is meant by water hammer, equations for pressure rise due to gradual wall closure and sudden wall closure for rigid and elastic pipes, and numerical problems are involved into that. This is what we are going to discuss in this session. I'm going to do only the introduction part so that you are well versed with the nomenclature, the words that we use in this particular arena. Okay, what is pipe and pipe flow? We'll see that. So it is a conduit through which the fluid flows under some pressure, generally circular in cross section. The conduit will be having a cross section of circle, right, so that it is a pipe like that, or you can have any fancy shape. One more interesting pipe section that is shown is oval shaped, or you might have seen in steel square cross sections, right? It can be triangular, it can be trapezium, whatever it is, but it has to be closed, and fluid, when it flows, it should cover the full of pipe, then only it is called pipe flow. If there is a flow which is partially flowing, then it is not a pipe flow. So this is one very important thing that one should know, right? As the fluid flows, it has to overcome frictional resistance. Obviously, when the flow occurs, it will be overcoming, or it should be overcoming, the frictional resistance along the periphery. When the flow is occurring, it has to come out, and in the sense it has to overcome that friction. Okay, then friction between layers of flow, and also friction between flow and solid boundary of the pipe. Obviously, if you consider layer by layer, right, between the layers there is a friction which is viscous friction, liquid friction, and then the friction between the solid surface along the periphery and the fluid, it is also viscous friction, but it is a boundary friction, right? This is a layer friction. Both the frictions have to be overcome by the flow, right? In doing so, obviously there will be energy lost. That is what we said, that energy loss in pipe flow. Energy is lost in overcoming the friction. Okay. Then what? The amount of energy depends upon, means the amount of energy that is lost depends upon the type of flow. What type of flow? It's either whether it is a laminar flow or turbulent flow. Right? What is meant by laminar flow? What is meant by turbulent flow? We'll see it further. Depending upon relative magnitude of internal and viscous forces, inertial, not internal, inertial and viscous forces, the type of flow is classified. Now, to identify whether it is a laminar or a turbulent, what you have to compare? You have to compare inertia force and viscous force of the flow, right? Of course, we'll be dealing with this in the next few slides, right? So, which is more, depending upon that, the laminar or turbulent flow? If the inertia forces are more, then we classify it as turbulent flow. If the viscous forces are more, then we call it as a laminar flow. Laminar flow will be slower, neat, layered flow, whereas turbulent flow will be intermixing, right? Noisy flow, rough flow. The type of flow is classified. Let us see. A non-dimensional number, how it is done is, a non-dimensional number, namely Reynolds number, is used to classify the flow into laminar or turbulent. So to classify the flow into laminar and turbulent, we'll be using what is known as Reynolds number. Now once you classify, we'll be knowing energy loss, whether it is less or more. Okay. Here there is Reynolds number expression that we have to do. Reynolds number is defined as, what is Reynolds number? It is defined as the ratio of inertial forces to viscous forces, right? So denoted as capital R, R with a suffix E, Reynolds number. It is force due to inertia divided by force due to viscous, right? Because of force to force ratio, the Reynolds number will not possess any units as such. It is pure number. That's why it is called number. Just a number, right? Now what is inertia force? You know that whenever there is a mass of a fluid which is flowing with some acceleration, that m into a is known as inertia force. What is viscous force? There is a shear stress because of viscosity multiplied by area gives you viscous force, Fv. We have done it in earlier classes, if you remember back. Shear stress developed because of viscosity into the area gives you viscous force. Now how to calculate mass into acceleration? Mass is calculated as density of the fluid into volume. You know this. Density of the fluid into volume gives you mass into acceleration divided by the tau by Newton's viscosity law, mu into du by dy. Tau is equal to mu into du by dy, where mu is dynamic viscosity, Pascal seconds is the unit of measurement, du by dy is a rate of strain, du is a velocity rate, dy is incremental distance, right? So the rate at which the velocity changing as far as distance is concerned, that is du by dy, or we used to replace this ratio as v by t also, right? So that multiplied by area gives viscous force. Now further, this rho is kept as it is. Volume is nothing but L cube. Volume is length into breadth into height, that is L cube. Acceleration is L by t squared. Meter per second squared would be the units. That's why it is L by T squared is the dimension. Mu I have kept it as it is. Du by dy is V by T or V by L, because it is velocity divided by distance, V by L. The area is L squared. Now if you simplify all this, it is becoming rho L cube divided by mu V T squared. Okay, this T squared has come over here. Phi is kept as it is. This L and this L goes with this L square, so we'll be left with rho L cube mu V T squared. Further, you know that L by T is a V. Because of that, L squared by T squared is kept as V squared. One L is remaining there. This V is kept as it is. One of the V goes. So final expression for Reynolds number would be rho VL by mu, or generally it is written as VL rho by mu. So rho or R Reynolds number is equal to VL rho by mu. That is how we remember. VL rho by mu is the expression for Reynolds number. But mu by rho is a kinematic viscosity, so VL by nu is also a Reynolds number. So this is kinematic viscosity. So mu by rho is kinematic viscosity. So VL by nu is also a Reynolds number. So V is called characteristic velocity of the flow, right? And then L in the expression L is known as characteristic length. If it is a pipe flow, then it is a diameter. If it is an open channel flow, then it is a depth, right, in the channel. Mean size of the sediment in case of a flow through porous medium. Depending upon the situation, you have to fix up what is L. In case of pipe, it is simply a diameter. So if you are talking in terms of pipes, then it will be VD rho by mu. D is the diameter. Okay, we'll see that. Now for pipe flow, if Reynolds number is, you can just see here, if Reynolds number, if this ratio is less than 2000, less means what? The inertia force is less and viscous force is large. The ratio has to be less in the sense the magnitude of viscous force has to be large, the inertia force value has to be less. When the viscosity is more, then it will be laminar. So R is less than 2000, then the flow is laminar. If R is greater than 4000, in the sense there is a dominance of inertia force compared to viscous force. The numerator is becoming more and more compared to the denominator. So when it is becoming 4000 and above, then it is a turbulent flow. And if it is between 2000 and 4000, you will not be able to classify clearly whether it is laminar or turbulent. So we say that it is transitional flow. You cannot decide clearly whether it is laminar or turbulent. Okay, these numbers are only for pipe flow, right? Suppose if you are talking about open channel flow, the values of R to classify laminar and turbulent will be different. And then likewise for different situations, the value of R will be different. But the R general expression remains the same, VL rho by mu, velocity, characteristic length, density divided by viscosity of the flowing liquid. Okay. Now energy losses in pipe flow. There are two major energy losses, two major groups of energy losses: simple, major loss and minor loss. The naming is quite simple: major loss in pipes, minor loss in pipes. One more very simple thing is, whenever we say major loss, it is because of frictional head loss, and because magnitude wise it is much larger compared to minor loss. That's why it is classified as minor. This is classified as major loss, right? Many a times this minor loss is neglected. If you consider clearly major loss, it is more than enough. That's what you should remember, right? Energy losses, two groups, major and minor. Major means frictional loss, minor means there are list of losses. You can just see here A, B, C, D, E, F, G, H, all these are minor losses. Major loss is only one frictional loss, it is due to friction, right? Now under minor loss you have for syllabus loss due to sudden expansion or sudden enlargement in the pipe section, and it is given by V1 minus V2 whole square divided by 2G. We are going to derive this equation anyway, right? Energy loss due to sudden contraction, it is multiplier is 0.5 V2 squared by 2G. Then energy due to gradual expansion or contraction. Look here, what the terminology means is there is a pipe coming, let us say, and suddenly the pipe diameter is increased. This particular case is known as sudden expansion. The flow is occurring this way. So it's not gradual, sudden. So that is the first case. There will be energy loss because this water tries to go that way and this try to go this way. So here there will be a stagnant liquid which will be there. Because of that there will be some energy loss, eddy formation we say. The flow gets mixed up like that and then it gets rotating over here and then stagnant there, but the flow will be continuous in this section. So because of that there will be some energy loss. That is what it is called sudden enlargement. Sudden contraction is reverse flow. If you have got a diameter, right, suddenly the diameter is decreased and then the flow is occurring. In such case it is straight away 0.5 V2 squared by 2G. The flow is occurring this way. Now the meaning of V1 V2 is in case of sudden enlargement, velocity with which it is flowing over here in smaller diameter V1, and when it gets into larger diameter the velocity is V2. It depends upon both the values of V1 and V2. That's why it is called V1 minus V2 squared by 2G. But in case of sudden contraction it is 0.5 and it is depending only on V2 squared, not V1. In this case when it is sudden contraction, this will become V1, this will become V2. So after contraction whatever velocity that it is possessing, that is a part of expression as far as sudden contraction is concerned. Now loss due to gradual expansion and contraction. So if the pipe is very gradually increasing in its diameter and then it's going ahead with the same diameter, so it is a gradual. In such case it is just K, the multiplier, a reduction factor, multiplied by V1 minus V2 squared by 2G. Then you got loss due to bends, loss due to fittings, loss due to obstruction in the pipe. All these, if you look at that, they are K multiplied by V squared by 2G, right? You got a pipe and then maybe there is a valve involved, there is a tap involved, there is some obstruction. In such cases a reduction factor K multiplied by V squared by 2G gives you the loss in those, right? There is no change in the diameter, but there will be some obstructions. Because of that it will be K multiplied by V squared by 2G. As there is no change in diameter, it is all just V, not V1 or V2, right? Now loss due to entry, it is called entry loss. So this is 0.5 v squared by 2g. So in a tank, suppose there is a tank, right, and then the water is entering into a pipe, let us say like that, and this is a tank wherein there is a standing liquid, and when it enters here there is no velocity. When it enters into pipe, obviously it will be having some velocity depending upon the head as well as diameter of the pipe. So v1 or v, let us say, not v1, v, so that v squared by 2g multiplied by 0.5 gives you entry loss. This entry loss and sudden contraction are similar, 0.5 v squared by 2g 0.5, because here also you can think of it as a sudden contraction itself, right? 0.5 v squared by 2g. Now loss at the exit from a pipe means, suppose here there is an end of a pipe, the velocity is v. When it comes out, right, it will be possessing some velocity v squared, v. So energy will be v squared by 2g, but when it comes out, all that energy is gone, right? So whole of kinetic energy is lost when it comes out of the pipe, right? The no more that velocity will be there, it just dumps itself. Because of that, the loss due to exit would be whole velocity head is lost. Okay, this is a major slide. Energy loss, there are two major losses, two groups of losses: major loss, minor loss. Major is frictional, minor you got so many of them, and among them sudden enlargement, sudden contraction, loss in bends, fittings, obstructions, loss at entry, loss at exit. These are the things to be remembered. It's easy to remember also anyway. Okay, head loss due to friction or Darcy-Weisbach equation. There is a derivation, we'll go through quickly. It's not big derivation, very simple. We have considered a pipe of diameter d. So when you got a discharge, there is a velocity v. Because of the same diameter, it is v1 and v2 are same. The spacing between 1 and 2 is length L, right, and it is kept horizontal. Now by Bernoulli's equation, the total energy at section 1 should be equal to total energy at section 2 plus the energy loss. Because it is a real fluid, we have to consider loss due to friction. That's why there is HF or HL, head loss due to friction. Okay, so you can just see P1 by gamma V1 squared by 2g plus Z1 equal to P2 squared by P2 by gamma V2 squared by 2g plus Z2 plus head loss due to friction from 1 to 2 HL or HF. Because diameter is same at 1 and 2, as I have told you, the velocities are same, v1 and v2. So what happens is these two expressions, they cancel off. v1 squared by 2g, v2 squared, right? v1 is equal to v2. Also z1 equal to z2. Because I have considered horizontal, the level of 1 and 2 is same. Because of that, this goes with this. So you'll be left with P1 minus P2 by gamma equal to HF. So that is what we get. The head loss due to friction, how does it affect? It affects by changing the pressure at this point and at this point. That's what. Now let F dashed be the frictional resistance per unit area per unit velocity. Then the force due to friction. Okay, now this is frictional resistance is per unit area per unit velocity, F dashed. So if that is the frictional resistance, I have to multiply it by area, multiply it by velocity, so that I get frictional force. So frictional force is given by F dashed multiplied by what is the area. Now when it moves, now look at that, from 1 to 2, right, it is cross sectional area is cylindrical, right. Peripheral, there will be area, that is pi dl. Pi d is circumferential length multiplied by L gives you that circumferential area, cylindrical area, so that is pi dl. That is the fluid is in contact with all that area, that's why it is pi dl. And then the velocity is v, and it is raised to n, because if it is a turbulent flow, you got n is equal to 2. If it is a laminar flow, it will be almost equal to 1, right. So frictional force of resistance is F dash pi dl phi squared. Okay. Now the same thing is shown as with forces, right, free body diagram kind of. So this you can take it as L, the length L, diameter is D. Now when you take a section here, the pressure force acts on this element, because it is a free body diagram, this is separated out. If you see, pressure will be acting from outside like that, P1A, and for this particular piece of pipe, the pressure will be acting from the other end, right. So P1A this way, P2A this way. Frictional resistance along the boundary will be acting in a reverse direction. The flow is this way, flow is this way. So equation can be written as, for sigma fx, right, which is P1A, A is cross sectional area of the pipe, minus P2A minus Fr equal to 0. We assume that there is no accelerated motion, because of that resultant force acting on the liquid has to be 0, right. Okay, further we'll see the same equation is written slightly in a changed form. P1 minus P2 into A is equal to Fr, or frictional force, or P1 minus P2 is equal to F by A, frictional force divided by cross sectional area. Now dividing by gamma on both the sides, it becomes P1 minus P2 by gamma is equal to 1 by gamma F by A. Now what is this P1 minus P2 by gamma? It is nothing but HF, head loss due to friction. I have put that is equal to 1 by gamma, this frictional force which we have made it here, F dash pi dl phi squared, that is there, divided by area of the pipe is pi d squared by 4. I have considered circular pipe with a diameter d. So F dash by gamma, pi cancels off, one of the d goes, so 1d remains in the denominator, lv squared, right. So 4 F dashed by gamma lv squared by d, that is what remains. Now substituting for 4 F dashed by gamma as F by 2z, there is a substitution, right. Just to put it in a simple format, substitute 4 F dashed by gamma as F by 2z, then what happens is HF becomes, this is F by 2g, this LV squared by 2, LV squared by d is there. Now here this F, plane F is known as friction factor, right. Now friction factor, if it is, if the equation is written as 4 FLV squared by 2ZD, I have written it below here. If it is given in many books, they give that way, then this F will be known as coefficient of friction. If it is plain FLV squared by 2ZD, then it will be called as friction factor. Anyway, head loss due to friction HF is given by FLV squared by 2ZD. Now what is V? V is nothing but the velocity of the flow in the pipe. So V is the discharge divided by pi d squared by 4. Now if I substitute for V in terms of Q, this becomes FL by 2GD. V squared is replaced as Q squared pi squared d raised to 416. If you simplify, you will get 8 FLQ squared divided by G pi squared d raised to 5. Even this expression is very useful expression for head loss due to friction. If velocity is known, then FLV squared by 2GD is fine. If directly in terms of discharge you are talking about without calculation of velocity, in such case it will be better to use this equation, which is 8 FLQ squared divided by G pi squared d raised to 5, right? So that is head loss due to friction and Darcy-Weisbach equation. Very familiar, very often you are going to use this as a civil engineer number of times, right? So that is friction loss in pipe. Okay, there I think we'll stop. We'll continue afterwards.